Let's go ahead and talk about nuclear fission. We previously learned what nuclear fusion is. Let's go ahead and talk about nuclear fission. You can think about the word fission as splitting up. What are we exactly splitting up then? Well, nuclei. Heavy nuclei, that is to be exact. We said previously nuclear fusion is when you mix up or when you fuse two light nuclei to create a larger nucleus. Nuclear fission, on the other hand, is when you split up a heavy nuclei, especially things that have at least 83 protons, into smaller parts. So, how many types of fission are there? Fission can be divided into two types. There are either induced fissions, fission reactions, or spontaneous fission reactions. Now, induced fission reactions happens for knowledge nuclei or things that have at least 83 protons. So, what things have at least 83 protons? Well, the elements in the periodic table that start from 83 and above, and the most famous example are things like uranium. Specifically, uranium-235, which happens to be a fissionable material that can be used in nuclear power stations. Spontaneous fission reactions, on the other hand, happens randomly during the radioactive decay of particles of these heavy nuclei. So, for example, during the alpha decay of uranium-238, we see it being broken down into smaller parts. The topic of discussion for today is, of course, the induced version of this reaction and how it works in a power station. Well, it happens in such a way which is quite easy to understand. Imagine a neutron is shot at a uranium atom. This uranium atom usually is uranium-235 with an atomic number of 92, of course. What happens then is this causes the uranium to be very unstable. And once it becomes very unstable, it undergoes the fission reaction to produce three main things: 92 krypton, 3 neutrons, as well as a barium atom. And don't forget the main thing: a huge amount of energy. The amount of energy that is going to be released can usually be calculated using Einstein's energy mass equivalence, E equals to mc squared. And in power stations, generally they take the heat of that energy, and you can think about it as they convert the water into steam, and then the steam can then be used to turn a turbine, which turns a generator, which in turn can generate electricity. One of the main points that are quite interesting about nuclear fission is the fact that it's a kind of eco-friendly process because it doesn't really produce any greenhouse gases. But the process of containing the leftovers of the nuclear reaction is actually quite dangerous, and it's one of the negative points about this. Now, let's not forget about what goes on in the reaction. These 3 neutrons that are released are then allowed to hit other uranium atoms, and they go on and they produce their own reactions as well, right? So more neutrons and more energy is released, and again, the neutrons hit other uranium atoms, and this reaction can go on, which results in something called a chain reaction. The chain reaction that is then basically going on should then be stopped by things in the nuclear power station, which are usually boron rods, which happen to kind of absorb neutrons, which will slow the reaction down. They're actually called control rods, and they're usually made up of boron or cadmium. Now, that is not out of interest for us for now. We just want to learn how to write the equations of nuclear fission. Well, the neutron is added to uranium-235 with an atomic number of 92. What is created is barium-56 as well as krypton and the 3 neutrons. Usually, in balancing out these equations, you'll be given one of these things. You'll be given like most of these things, and you'll be asked to find one missing value. And you can find the missing value by considering the law of conservation of energy, and as well as atomic number and the nucleon number on both sides. So basically, here krypton, which has a atomic mass number of 92, barium has a mass number of 141. The atomic numbers match on the right side. They're both equal to 92. And if you add the atomic numbers on the left side, they also add up to 92. If you add up the mass numbers on top, there's 3 neutrons, 92 on this side and 141 here. That adds up to 236 on the right and 236 on the left, which shows that the law of conservation of energy is actually followed here. Now, if this chain reaction that I explained at the top goes on in a controlled manner using the control rods, then you can use it to produce electricity in power stations. However, if it's uncontrolled, then you would have explosions, which can then be used to create atomic bombs. And that's the uncontrolled format of it. Let's go ahead and do a couple of examples on the reactions of nuclear fission. So let's say uranium-235 reacts kind of with a neutron, and what is produced in the fission reaction is rubidium-37, mass number 96, as well as cesium-137, 55. What is going to be the next element that'll complete the reaction? Well, as you can see, the atomic numbers match. They're equal to 92. So it's not going to be a new element for sure. The only thing that we can come up with is a neutron, which has a mass number of 1, atomic number of 0. But how many neutrons exactly? Well, let's count the mass numbers on top. 137 plus 96, that's going to give us 233. We got 236 here, so we're talking about 3 neutrons because that'll complete the reaction. If you add 3 to this, you get 236, which will make both sides of the equation be equal to each other. So that is the process of nuclear fission. Let's go ahead now take a look at a problem in which we have to actually calculate the energy released. So let's consider the original equation of nuclear fission. Example number 1. Let's calculate the energy released in the reaction that is given below. 235 uranium reacts with a neutron to give out barium-141 plus krypton-92, as well as 3 neutrons and energy. So what we're supposed to kind of calculate in this question is the amount of energy released. Now let me give you the masses of everything that is required here. So let's say uranium-235 has an atomic mass unit of 235, let me be exact, 0.439 atomic mass units. Barium has an atomic mass of 140.9144 atomic mass units. Krypton, on the other hand, has an atomic mass number of 91.9262 atomic units. And the atomic mass of one neutron is approximately 1.008665 U's. So, the first thing you want to do is we know that from Einstein's energy mass equivalence, energy is equal to the mass defect times the speed of light to the power of 2. The speed of light is just 3 times 10 to the power of 8 meters per second, and it's a constant number. So what happens from here onwards is E is equal to the mass defect, which happens to be, if you were to kind of find the mass defect in this part of the problem, you basically have to add up all the masses on the left side and subtract them from all the masses on the right side. So you would basically have to subtract the mass of uranium. So delta M would be 235.0439 plus the mass of one neutron, 1.008665 665 minus the mass of whatever's on the right side, so the barium, krypton, and the 3 neutrons. So minus 140.9444 minus 91.9262 minus 3 times the mass of 1 neutron. So if you do that, you get delta M is equal to 0.186 atomic mass units. So you can then multiply the mass defect by 931.5 if you want to get the answer in mega electron volts. That'll give you 173 mega electron volts. But if you want to get the answer in joules, you should convert this into kilograms. And we know that 1 atomic mass unit is equal to approximately basically 931.5 mega electron volts. So you could do that to write the answer in mega electron volts. But if you want to get the answer in kilograms, you have to convert the atomic mass unit to kilograms first. And 1 atomic mass unit is about 1.66 times 10 to the power of negative 27 kilograms. So you'd have to multiply this by the mass in kilograms. That will give you 0.186 times 1.66 times 10 to the power of negative 27. You will get 3.08 times 10 to the power of negative 28 kilograms. And if you multiply that by the speed of light to the power of 2, you'll get the answer in joules, which happens to be 1 second. So that happens to be 2.7 times 10 to the power of negative 11 joules. So the answer in joules would be 2.7 times 10 to the power of negative 11 joules. So quick cautionary reminder here. If you want to get the answer in joules, then you should actually convert atomic mass units to kilograms, and you do that by multiplying the atomic mass unit by 1.6 times 10 to the power of negative 27 kilograms. And you also use the speed of light, use c. But if you don't want to convert it and get the answer in mega electron volts, so in MeV instead of joules, which is this process, you should not convert anything into kilograms, and you should just multiply the atomic mass defect by 931.5. That's it. Thank you for watching.